Here we're going to have a look at the continuous rate of reaction, or sometimes referred to as initial rate of reaction. So this is a method to find out the rate of reaction of a reaction. So we're going to have a go at looking at the method for this. So let's start off here. Here's the fundamental concept. You need a timer. You've got something to measure, let's say volume of gas, easiest way to do it. You've got gas that's being produced and sent up to the gas syringe, and you've got reactants. Let's say it's a metal and acids, magnesium and acids are quite a standard reaction for this. Now that hydrogen gas is going to be pushed up here through pressure, and using pressure it's going to move the syringe back, and this will give you a reading for the volume of gas produced. Now if you're doing a continuous method, what you're going to do is you're going to have a stop clock. And on that stop clock, you will be recording every, let's say, a regular interval. So let's say every 5 seconds, the volume of gas that has been produced. Now, the bit that's quite tricky with this is that the rate can vary quite dramatically, especially when you do things like concentration, because 0.1 and 2 molar will have very, very different rates, which will mean that actually with this, you'll need to do some pilot practicals, sort of preliminaries, so you know what volumes to use, what masses of magnesium, and what sort of values you can expect to get from the highest and the lowest concentration, so you don't sit there for hours waiting for a volume of gas to be produced from a low concentration, or the whole syringe being filled up within 5 seconds of actually mixing them together, 5 or 10 seconds, whatever your interval is. So that's what you're going to be. That's the way this generally works. So every sort of 5-10 seconds, it might be 30 seconds, it might be a minute, depends on the pilot study, you take a reading for the volume of gas produced. Another way to do this is to use the mass. So in this case, I've got the same practical. I'm using a conical flask. There's a bit of cotton wool here, and as it reacts, the gas escapes through here, the liquid and the metal do not, and the mass will decrease. Now this is better for reactions like calcium carbonate and acid, mostly because the carbon dioxide has a greater mass than hydrogen. So the mass of hydrogen is 2, but 44 for carbon dioxide. So you will see a more noticeable change if the gas is heavier, or not heavier, but has a greater mass. So as the gas escapes, the mass goes down, and you have a stop clock here, and then every 10 seconds you record the volume. Now what you'll get in that case is a curve that looks like this, which is slightly different to how you'll, or the same concept, but we're going to have to manage that slightly differently to the previous one, because this is measuring loss of gas, not volume of gas produced. So once you've done this, you will get your axis, and on your x-axis you're going to have time, and your y-axis, let's take the original method, you're going to have volume. What you'll get is a curve that looks like this. Now you might do this several times with different concentrations. So if you use, let's say, a low concentration, the rate would be less and the curve would be below. However, it would never exceed, it would just level off at the same level. Okay, so you might get several curves on the same line for different concentrations. This method is much better for using with one concentration to see the initial rate. What you're then going to do is you're going to take a ruler and you're going to position it on the line, and if it's the initial rate, which it normally is, you're going to position it at 0. Now there's a trick doing this, and it's to get a clear ruler, so a see-through ruler, so you can see the line, and hold it up against the other line so no point of the curve overlaps with the ruler, so you see that you can't see any of the line on one side. And what you do is you use that ruler to draw a straight line, and it's a little bit wobbly there just because of the what I'm doing it on, but you draw a straight line. Now this gradient here, that is your initial rate of reaction. So what you would do is, you've got 0, 0 fortunately in this case, but let's say this is 10 seconds in and produce 50 centimeters cubed of gas. That would be, your initial rate would be 50 centimeters divided by my time, which is 10. So it would be 5 centimeters cubed per second, right? And that would be the initial rate of reaction. Now you might get asked a question where it says at time at 20 seconds, what is the rate of reaction? Now, as the concentration is decreasing because the chemicals are being used up, the rate of reaction will also slow down. So if you did that and you would draw another tangent at that point, so let's say it was here, again, it's a little bit wobbly, but let's say it was there, so that's 20 seconds. You would then do the same thing, but instead you now need 2 points. So I would normally take this point here, and let's say this point there, because we actually probably know that value. So times 0, and that's 20. So we're going to divide it by 20 seconds, and then the volume by which it rises. So this volume here, by which it rises, that will be what I divide my 20 seconds by to get my rate of reaction. If I did it using the other method, which would be sort of a gas loss method, and there are variations of this, so you need to be aware because they can ask you different variations of what volumes you record. You would do exactly the same thing, except the curve would be down. So instead you would have to draw your tangent like this, or you would have to invert it by putting 1 over.